any new formulas, we'll use the ones we already know, but we're going to use some trig identities that we should know, hopefully from trigonometry, but I'll remind you of them here. And then we're just going to look at, well, what are some techniques we can use? So not necessarily new formulas, but how we can apply them to the different forms that we're going to see today. So today we're mainly going to deal with sine and cosine. The second half tomorrow we'll deal with the other trig functions, but today we're going to look mostly at just the sine and cosine ones. So I'm going to give you a couple formulas you should know from trigonometry. I'll give you the double angle formulas. We'll use these every once in a while from trig. So let's see if you remember these. The sine of 2x, called double angle formulas because they have 2x in there, so it's like double the angles. Anyone know what sine of 2x is equal to? Good, so you should know that one. So 2 sine x cosine x. You should also know what cosine of 2x is equal to. This is the one that has a couple options. Anyone remember any of them? Cosine squared minus sine squared, right? That's one of them. What else could it be? 1 minus 2 sine squared, good. And 2 cosine squared x minus 1. Yeah, this is one that has several options, mainly because you can always substitute like cosine squared with 1 minus sine squared, or sine squared with 1 minus cosine squared, and you get these other options here. So that's why we get some different options here, and those are the different formulas there are. So sine of 2x mainly has 1. This one has 3. Sometimes we'll just have to look and see what's the best option in the situation that you have, but any of those 3 are true. The other ones we should know are called the power reducing formulas. They reduce it from a squared down to a first power. So they're actually, they use a lot of this identity here, the double angle formula, and they kind of solve it for sine squared and cosine squared. So it's actually these formulas kind of solved for the other piece. So I'll give you the first one here, that's for sine squared. So sine squared is equal to 1/2 1 minus cosine of 2x. So that's like if we took this middle formula here and solved it for the sine squared, that's what it would be equal to. We call it power reducing because it's reducing it down from a squared to cosine to the first. It has a 2x now, but it is to have a first power, which is much easier for us to integrate. And there's one for cosine squared as well. It's almost the same, but with a 1 plus cosine of 2x. So the difference is a plus there. Those sound familiar at all? Maybe, kind of, okay. And sometimes you'll see it, you know, the 1/2 distributed in or not, but I'll just leave it in that factored form. What else? So we'll use some of these, we might use those, and of course just the Pythagorean identity. I'll make a note of that. You should know that one. Most people remember that one, but sine squared plus cosine squared equals 1. And we can manipulate that to solve for sine squared or cosine squared, but that would be the other one we could use there. Okay, so these are kind of their relationships. We're going to use some of these as we try to integrate the trig functions. So refer back to them if you need to. Hopefully you remember your derivatives. What's the derivative of sine? We know that, right? Derivative of sine is cosine, right? Derivative of cosine is negative sine. So let's make sure we know which ones have a negative or not. So let's go ahead and look at a couple examples. So we're going to look at integrating. Again, like I said, a lot of these are products of trig functions, sine times cosine with different powers on them. This one we'll start with some easy powers. Just here's 2 sine x cosine x dx. Yeah, what do you think? Where would I start on this one? What do you think? Okay, so the 2, we could take that out for sure. What else? Okay, a u substitution, what would you do? Okay, let's go with that. That seems like it might match up pretty well, right? So we do a u substitution. U is sine of x. du is cosine of x, and that will match up to the other piece of our integral. So this seems pretty straightforward. I could just do a u substitution here. So if I do that, then I get 2, this is our u, and the rest is our du, and I just need to integrate the u. So what will I get when I integrate u? That should be what? U to the what? U to the second over 2, right? Okay, it's coming back to you now. It's been a long weekend. All right. So yeah, that's just u squared over 2, just a power rule there. It's here to the first, so we're going to add 1, divide by 2. The 2's then will cancel, and then we'll just get u squared plus c, but u was originally sine, so this should be just sine squared of x plus c. Okay? So sine squared of x plus c, and the 2's will cancel there. The 2 I left right here, right? But it canceled with the 2 in the denominator because you get u squared over 2. So, yep. Is it the only way I could have done this one? Yeah. Is there an identity for 2 sine x cosine x? Look back at the front. What do we say 2 sine of x cosine of x could be the same as? Sine of 2x. Let's integrate it like that and see if that could change our answer. Or hopefully I will get the same answer, but we better check. So 2 sine of x cosine of x, I could rewrite as sine of 2x, right? If it's sine of 2x, is that pretty easy to integrate? Yeah, what's the integral of sine? Negative cosine, right? So I could get negative cosine here. Do I need to adjust anything for the 2x? Yeah, you have to divide it by 2, right? So you could do a u substitution here. U is 2x. The du would be 2, so you're going to have to divide by that 2. So, but remember, the quick way is just divide by the derivative of the inside there. So I get negative cosine of 2x over 2, right? Plus c. Is that the same answer as what I got up here? They seem a lot different, right? Are these two in fact equal, or did I mess up somewhere? It's still the same? Yeah, so let's check. And you may or may not write this part. You don't necessarily need to check in your homework, but you should be aware that if you get an answer that's possibly different, like an odd answer that's different from what's in the back of the book, doesn't necessarily mean it's wrong. You better check and see if it's the same. So remember, what did we say their identity was for sine squared of x? Did we say there was an identity there? We said it was 1/2 1 minus cosine of 2x, didn't we? Well, that's the same as 1/2 minus 1/2 cosine of 2x. Is that the same as what I have here? This part is, right? Exactly the same as that. What's this 1/2? That's the c, right? That's the constant. So these are in fact the same. So they are in fact equal. This piece is equal to that piece with this extra constant on that. So these turn out they are actually the same. They just differ by a constant. So that's the only difference there is the c. So that's kind of interesting that I can get two different results that kind of look like they're not anywhere close to being the same, but they in fact are based on this definition, this identity that we have. So keep that in mind. This is exactly equal to that with the constant of 1/2 here. So that's kind of the c is really the arbitrary difference like Jonathan was thinking. They're actually the same. It's the c that's making it seem like those are different answers. So. Okay, so either of these would be legitimate answers, so whatever technique you would have used would be correct. So this is correct and this is correct. So sometimes there's more than one correct answer. Would
this only be correct if C was 0 for the sine?
And 1/2 for the other one. Yes, that would be true. So in this case, C would have to be 0, and this would make it 1/2. So if you had a different constant here, well, then that would change that constant, but it could still be a possible answer. So, yeah. Okay, so keep that in mind there, but those are both legitimate ways to solve that one. Okay, let's look at B. The integral of sine squared of x. Alright, so we don't have an integral for just sine squared, right? We know what it is for sine, but not sine squared. What should I do with the sine squared here? Any thoughts? What do you think? Do we have an identity we could use? Okay, let's try that. So let's try to use the power reducing, because we do have one for sine squared. See if that form puts it into something that's a little easier for us to use. So sine squared is equal to 1/2 times 1 minus the cosine of 2x dx. In this form, does it look like something I could integrate? What do you think? Can you integrate? Well, we can pull the 1/2 out. Could we integrate 1? Can we integrate cosine of 2x? Yes. So we should be able to do this. So let's go ahead and do that. So you could pull out the 1/2 if you want, and then just integrate the 1, and then the minus the cosine of 2x. What is the 1 going to give us when we integrate? X, right? What's the integral of cosine? Sine, right? Does it change to negative or anything? No, that just stays the same, right? So it's minus sine of 2x, but because of the 2x, what do I have to adjust by? 1/2, right? So you need to divide this by 2. And we'll do that over and over again, and you could do it with the u sub, but it's just easiest if the derivative of the inside is a constant that you just divide by that when you integrate. Okay. And then plus c. And that should be it, right? We're done. So these might be shorter than integration by parts, which is nice. So that's really all you need to do there. You can distribute the 1/2 in or simplify that if you want, but any form of that is fine. If you want to distribute, it would look something like this, but any form of that would work. Okay, so 1/2 x minus 1/4 sine of 2x should work there. Okay, questions on that one? Okay? Seems too easy, right? Okay. Let's do the next one. So this one has some higher powers for us to work with. This has the integral of sine cubed of x times cosine to the 4th of x. Okay, so where are we going to go with this one? Well, I definitely don't have any formulas for cubed or to the 4th, right? So what should I do here? Okay, we can definitely do that. So what if we did like a sine of x and maybe sine squared? And let's see, so we still have cosine to the 4th. You could do a cosine squared and cosine squared, but what if I just left it like this? And why would I leave it like this? Well, remember that one of these is the derivative of the other, right? So if I do a u substitution now, can you see it's the derivative that would show up? What would I let u be possibly? And its derivative would be there by itself. Yeah, there's the derivative, right? So what if I let u be cosine, and then I have the derivative has a sine right here? Let's think about why that would be helpful. So what if u was cosine of x? And then the derivative, well, technically it's negative sine of x. But the sine of x part is showing up here, right? So here this I could replace with a u, like u to the 4th, right? But I'm stuck with this extra sine squared. Is there a way to rewrite sine in terms of cosine? So everything could be written in terms of u. Is there a way? You could do power reducing. However, with power reducing, what kind of cosine do we end up with? It's a cosine of what? 2x, yeah. And it wouldn't necessarily be a cosine of just x. What's another way to substitute sine squared and replace it with some type of cosine of x? 1 minus cosine squared, right? So what if I split these up, and then I took sine squared and replaced it with 1 minus cosine squared? Let's see what happens here. Okay, so I'm going to do the replacement, 1 minus cosine squared, and then I'm going to go ahead and apply this substitution. Okay, so notice now I've written everything in terms of cosine except the sine I left because that's going to be my du. Okay, with a negative, so I'll put a negative out front. So I'm going to put that negative out front, and then sine of x dx, that's all du. And this is 1 minus u squared and a u to the 4th. Okay, so sine x dx gets taken care of with du and a negative. This cosine, that's going to be u but squared, and this will be u to the 4th. Now the question is, could I then integrate this 1 minus u squared times u to the 4th? Yeah, but what do I got to do first? Distribute, yeah. So this doesn't seem too bad. Once I distribute, I should be able to integrate this. So that's u to the 4th minus u to the 6th. And then I can just use the power rule on each of those. So let's see what that becomes here. If I have u to the 4th, let me start up here with Benham. What does u to the 4th become? Good. And Benham, what's u to the 6th going to be? Very good. Yep. So power rule, add 1 to the power and divide by that. And I just left the negative out front. So you could distribute that in now if you want to get rid of the parentheses or brackets. And what else do I need to do? Yeah, re-substitute u, right? So we go back in terms of x. That's exactly right. So this will be negative 1/5. So now this was cosine, so it'll be cosine to the 5th of x. And I'm going to go ahead and distribute, so that will make a plus 1/7. Cosine to the 7th of x plus c. And then you're done. So once we start getting, oh, question, I didn't do the power reducing here. Are you looking from here to here, or sine squared? Yeah, sine squared, I actually didn't use power reducing. I used the Pythagorean identity. So I used this one here. Do you remember that one? The sine squared plus cosine squared equals 1. And so that way, when I solve for sine squared, it would just be 1 minus cosine squared. And the reason I chose this one is to keep them consistent. Usually in the same integral, you don't want an x and a 2x, because then you can't use the u for the same thing. So that's kind of why I chose that one over the power reducing. So, yeah, good question. Other questions on that one? Okay, we're going to use this technique quite a bit in this section. So when you have higher powers, a lot of times what you want to do is kind of separate them down. If you can do like a u substitution, you might want to separate out a single one to save it as your derivative, and then write everything else in terms of what's left. Here it was a cosine. So that's kind of a technique we'll use, not just with sine and cosine, but some other trig functions as well. So here's kind of a similar case where here we have a sine squared, but cosine is to the 5th. So in this one, if I want to leave a single one out by itself, which one am I going to have to single out? Probably. Which type of powers do we have? Sine squared, I know I can use a Pythagorean identity for, right? So when I have an odd number, that's usually where I want to separate one out here. So let's try that. We're going to take sine squared. And a cosine to the 5th, we're going to separate as 4 times 1. So cosine to the 4th times a cosine of x. Okay, I'm going to separate kind of if there's an odd power, the odd one out. Even powers are easier to substitute for because we have Pythagorean identities, we have power reducing formulas. It's harder when it's an odd power, so that's when we'll usually separate that out. So if I separate that out and I want this to be my derivative, what should I let be u in this case? What do you think? Probably the sine, right? So that du then is cosine of x, right? Does it need to be negative on this one? No. So that should match up exactly. So there's my du, right? So if I want u to be sine, well, it's no problem to substitute the sine squared, but I don't want to leave the cosine in there. I want to do a substitution for that too. So how could I change cosine to the 4th of x? Well, I can, right? Because cosine to the fourth is just cosine squared again, right? Squared squared. So what if we wrote it as this? Cosine squared squared. Yeah, and then what can we substitute? Cosine squared is equal to 1 minus sine squared. So now I can replace it with a sine squared. 1 minus sine squared. So I'm going to go ahead and do that. Make that 1 minus sine squared. But there's still a squared on the outside, so be careful. So that becomes 1 minus sine squared, but we still have to square that because it was to the fourth. So okay, so I use this identity, and I'm going to use this substitution now. So sometimes I write that at the beginning so I kind of know what I'm working towards. So I know this is du, and now the rest can be written hopefully in terms of u, right? So Angie, help me out. What would that look like? If I replace all the signs with a u, what would it be? Right here, what would I have? So we're going to start plugging in the u's, and that's sine, right? So if I plug it in for this, what would it look like? U to the what? This one's just a second, right? Yep. And then what would it look like in here? 1 minus, this is u, right? So that becomes a u squared, yeah? And then what's all this? du, exactly. So that's what it will look like now. So you'll have the u squared, 1 minus, that's also u squared, but also square, and then a du. So everything's in terms of u and du. Hopefully I can integrate now. Joel, can I integrate this? Yeah, what would you have to do to simplify? Yeah, you have to square this, right? So you got to square it. Now we can't actually just go squared squared, right? You have to FOIL, exactly. So just be careful, FOIL that out. So multiply it times itself. I think you get 1 minus 2u squared plus u to the fourth, right? So 1, there'll be a negative 1u squared and another one, so they add together to negative 2u squared in the middle. And this will be a plus u to the fourth. So that would be the first step. And then we're close. Now what would I have to do, Natalie, in order to integrate this? To do one more thing to simplify. What do you think? So I FOILed this out. Now what? Getting close. Yeah. So we just need to get rid of the parentheses, right? So we can just have terms. Yes, that's it. So just get rid of the parentheses and distribute. So that's exactly right. So u squared minus 2u to the fourth plus 4, no, not 4, plus u to the sixth is actually what that is. So u squared minus 2u to the fourth, u squared times u to the fourth, you add those together and get u to the sixth. I think is what we have there. That look good? Okay. Once it's terms like that, once you've distributed everything out, you should then be able to just apply the power rule to each of those. So a lot of times we'll get these expressions like this. They're just algebraic though, so we should be able to FOIL, distribute, and then we can integrate. So Taylor, what are we going to get when we integrate? Apply the power rule here. What do you get for u squared? Good. And then what do you get next? Good. All right, looks great. We have our plus c. Riley, anything else we should do at the end here? Yeah. Plus substitute back the sign, right? So don't forget the sign was our u. So we're just going to plug that back in. So we'll have 1/3 sine cubed of x minus 2/5 sine to the fifth of x. And then plus 1/7 sine to the seventh of x. I almost ran out of room, but plus c will go on the end. There we go. Okay, so notice in the example C and D, we kind of did something similar. We have those higher powers of sine and cosine. The best thing to do is kind of single out the odd power and separate one of those out, and then really to write everything else in terms of whatever's left there, which would be the sine. And usually we can use that Pythagorean identity to help us as long as we have squared powers to do that. On the cube one, this one? Yes, this one has a negative, but these should have a plus, right? Only the middle term has a minus. Yeah, when we FOIL, only the middle term I think will have a minus there. So, yep. Okay, other questions on that? Okay, let's try one with some limits on it. So this one we're going to do the integral from 0 to pi over 2, sine squared times cosine squared. Now the thing that makes this one different is they're both squared. So there's no like odd power that I can separate out and use sort of for the derivative. So I could separate it out into cosine, but then I'll have like this extra cosine that isn't squared, so I can't really do a substitution for it. Does that make sense? So you can substitute one for the other if you have it squared, but if I split it up into cosine, I can't really make a substitution for the cosine. So, what else could I do with this one? Okay, you want to do power reducing on both? Okay, right, and they're both cosines, right? Okay, so he's suggesting let's do a power reducing on both. Okay, so what was sine squared was equal to 1/2, right? Just substitute that in. 1/2, what was it? 1, is that the one that's a minus? Yeah, 1 minus cosine of 2x. And the other one is 1/2, 1 plus cosine of 2x. So I'm going to do power reducing on both. And Joel did make the observation. They both have a cosine of 2x, which is good. Then at least they'll be the same trig function. So, yeah. So let's do a bit of simplifying here. Let's bring out the 1/2. So those would make a 4th in front. So we can do that and get rid of the fractions out front. But notice these are being multiplied together, right? So I'm probably going to have to FOIL that out before I can really see if I can integrate this or not. So let's go ahead and distribute this out. So let's see what I would get. I'd get a 1, right? What's going to happen to the middle terms? Yeah, they'll cancel. Plus cosine 2x minus a cosine 2x, those will cancel. And then I'll have minus what? Cosine squared of 2x, right? Okay, so good. We did power reducing, but notice we're still ending up with a squared. And I can't integrate a squared, right? I can integrate the 1, but not necessarily the squared. Well, what could I do now with the cosine squared? What are my options? Do I have something for cosine squared? Yeah, I got something, right? What could I do with it? We could do 1 minus sine squared or power reducing, right? Now 1 minus sine squared will still leave us with a what? A squared. And we don't know how to integrate the squared. But power reducing could bring it down so it's not squared anymore. So what if we did another power reducing on this? Okay, what would we have left? So if it's cosine squared of 2x, how's that going to work? It'll start with a 1/2, right? Remember, this is the identity. Cosine of 2x is equal, or x, right? Cosine squared of x is equal to 1/2, 1 plus cosine of 2x. That's what it is right now, right? Okay. So, what's going to happen when it's cosine squared of 2x in here? How's that going to change what's over on the right? Anything? Yeah, that's the relationship, right? So this doubles the angle over here. So if this is x, in the formula, it doubles it to 2x. So if we already have a 2x in there, what this becomes is cosine of 4x. It doubles that angle. So we can apply it to 2x, we just have to double the angle inside. So this becomes 1 plus cosine of 4x. Okay, so this is the original formulas with an x becomes 2x. So if you have cosine squared of 2x, that will become 4x. So you can adjust the formula like that. It doubles the angle. Now can I integrate these pieces? Hopefully, right? Do I know how to integrate 1.5? Do I know how to integrate cosine 4x? I should, as long as it's not squared. So I should be fine. Let's do a little bit of simplifying here before I go to integrate. Notice what we're going to have in the front here is 1 minus a half, right? If I distribute that, what's 1 minus a half? A half. And I can distribute this through and it'll be negative 1/2 cosine of 4x. So I'm just going to add those constant terms together in the front there. So kind of clean this up, distribute the negative 1/2 through, and then add the two like terms in the front. And then I hopefully am ready to go. Let's see what we get. So we've got the 1/4 out front. Okay, so what's the integral of 1/2? Taft, what will that be? If we integrate the 1/2. Yeah, but I'm still just put on the x, right? Because there's a constant, so 1/2 x. Jessica, what do you think about the 1/2 cosine of 4x? What's the integral of just cosine normally?
Just cosine would be negative sine.
And it would actually just be sine, right? The integral of cosine is just regular sine, not a negative, so you don't have to change that. So, yeah. So that will be sine of 4x. And then remember, how do we adjust for 4? Anyone remember what do we got to do if there's a 4x inside? Divide by 4, right? Or multiply by a 4. So now instead of 1/2 here, what will it be? 1/8. Good. Yep. There you go. Yeah, so the integral of cosine is sine. You don't have to change signs. And then you have to make sure, though, that you divide by the derivative of the inside, which is a 4, making that 1/8. And then we're going to go ahead and plug in our limit, 0 to pi over 2. So that would be the regular integral, but with a plus c, we're going to plug in our limits here. So let's see what we end up with. So here we've got 1/4. Let's plug this in. So we've got 1/2 times pi over 2 to start. And then plug in pi over 2 here. That would be minus 1/8 sine of 4 pi over 2. Minus 0. I like that. Makes 1/2 times 0 is just 0. And the 1/8 sine of 4 times 0 is also 0, right? Is everything? Okay, so this is 0. What's the sign at 0? 0. What's the sign here? This reduces to 2 pi. What's the sign at 2 pi? Also 0. So we really just have this first term. And it has a lot of fractions. 4 times 2 times 2. So pi over 16. Is what we have left there for our final answer. Okay, so that's all we have is that first term, pi, and then multiply 4 times 2 times 2. That will give you 16. Okay, so that actually worked. So Joel's idea of let's use power reducing on both of them, we definitely could do that. That worked out here. We did still have to FOIL and then use it again because we did still have a squared left. But having that squared, we can do another power reducing even if it's 2x or anything inside. As long as it's squared, we can adjust for that. It doubles the angle basically in the other side. And then we can integrate that. So we can integrate now anything cosine as long as sine, as long as it's to the first power. It has just a constant with x in there, we'll be able to integrate that. So power reducing a couple times. Questions on that one? Okay, there. Okay, let's do one more here. Let's see what's going on with this last one here. So that one, notice, happened when they were both even powers. That really is where you have to use power reducing on both of them because there's not kind of an odd power to separate out and uses a u and a du. So F has another case where they're both odd. Okay, so this is where they're both odd. So we've looked at even with an odd. We looked at even with even, and now we have like two odd powers together. So what are we going to do here? What do you think? Sine cubed and cosine to the fifth. What are our options? Okay, separate out. You think both a sine and cosine? Okay, what if you did that? So you had sine squared and a sine. And then you'd have cosine to the fourth and a cosine. Now I have both a sine and a cosine, so I could probably do some sort of u substitution, right? Which one would you choose to be your u and your du? What do you think? What do you want u to be? Sine. Okay. So if you choose u to be sine, then du is the cosine part, right? The cosine of dx. So this part I'm leaving out as my derivative. So obviously these can be written as u's, but I'm going to then have to change the cosine into terms of sine so I can write it as a u, right? So if I've chosen u to be sine now, then I have to change the cosine to the fourth into terms of sine. That shouldn't be too hard though, right? Do we know how? Yeah, exactly. And actually I might combine these back. If I'm not going to use this sine, I'll just leave it as sine cubed. So remember, we can make this into sine squared squared, or cosine squared squared. And then use the Pythagorean identity, which is 1 minus sine squared. Remember, I'm kind of separating this out, leaving that cosine x dx because that's kind of my du. So now I'm trying to write everything else in terms of the sine, so those can all be written as u's. So now let's go ahead and make the substitution. So I used a couple identities here, just kind of simplified, then used an identity. Now I'm going to go ahead and put in the u's. Okay, so let's see what that's going to look like here. McKelty, if we now start replacing signs with u's, what is this going to look like? Good. Yeah. Squared. And then what's left at the end? Du, exactly. Okay, so there's a u, so that's u to the third. This is u, so 1 minus u squared, that's still being squared, and then du. Okay, and hopefully then this is something I can integrate. How would I need to integrate this? Kobe, what would I have to do first? Yeah, what would you do to simplify? Exactly, FOIL this and then distribute u cubed, just like we kind of saw before. So foiling this out is 1 minus 2u squared plus u to the fourth, and then distribute in the u cubed. So that'll be u cubed minus 2u to the fifth plus u to the seventh, all times du. And then we just integrate. So Nathan, what would I get when I integrate this? Yep. Yeah. 2/6, which becomes 1/3, good. Yep, plus 1/8 u to the 8th. Looks great. Okay, good. So 1/4 u to the 4th, this becomes 2u to the 6th over 6, which reduces to 1/3, and then 1/8 u to the 8th plus c. Jonathan, anything else I need to do here? Put the sign back in. So 1/4 sine to the 4th x, 1/3 minus 1/3 sine to the 6th x, plus 1/8 sine to the 8th x, and your plus c. Okay. So yeah, that's what we end up with here. So when it's an odd power, here we kind of separate one out. Now, could I have at the beginning here chosen to let u be cosine instead? Do you think it would have worked out? Probably, right? If u was cosine, then I could use du as negative sine of dx, and I would just have to have changed the sine squared into 1 minus cosine squared. So in this one, it turns out there's kind of two ways you could have solved it. When there's an odd power, you can actually separate either one of them out and decide to be one is u and one is your du. If I had done that, my answer actually would be in terms of cosines. And it would look different than this, so you'd think, oh, those aren't the same, but actually by identities, they would be equal just because of the plus c would make the only difference there. So this one with odd pairs, there's actually sort of two options that you can go with, but you have to separate one of them out and put everything in terms of the other one. So those are kind of the different things we can see with sine and cosine and multiplying the powers together. So I'm just going to write some of the strategies we use so you can jot those down. So when you're evaluating sines times cosines and you have these powers on them, sine to the m, cosine to the n, here's some strategies to use. If the power of cosine is odd, so not the other one, but cosine is, that would be the one you would separate out and use cosine to be your du. So we would save one cosine factor. I'll just kind of write it out here. And then use this identity to write everything else in terms of sine. Then you just substitute on this one. If you save a cosine, then u would be sine x, and du would be your cosine of x. Okay. So you'd save that one cosine out to act as your du, and then everything else would have to be written in terms of sine and substituted with u's. So that would be the strategy there. If the power sine is odd, then that's the factor you save out. So save one sine factor, and then use the other identity, sine squared equals 1 minus cosine squared, to write everything else in terms of cosine. So then you would do kind of the opposite substitution. U now would be the cosines, and the du would be the sine that you've saved out. And it will have a negative in front, but you can adjust for that. So, okay, so that's kind of your strategy if sine is odd, but cosine's even. And then we saw the other cases, the other two cases, when they're both even, that makes it a little hard. You basically have to use the power reducing identities instead. You can't really save one factor out, because then you're left with just a single factor, a factor to the first power that you can't then do a substitution for. So if the powers of both sine and cosine are even, usually you have to use the power reducing formulas. So usually you have to do the power reducing formulas on both, and sometimes more than once. So that's the example we saw earlier. We used the power reducing formulas on them both at the beginning, and then we ended up using it again in the next step. So you may need to use it more than once. And finally, this is the last case we saw where they were both odd. And this is the one where really you have a choice of what to save out. So you get to choose, I want to save this factor out to be my du, and then write everything else in terms of the opposite one. So leave one of the factors out for your du, and then write everything else in terms of the other trig function. So this is the one where you get to choose. So if you leave the cosine out, then you need to write everything else in terms of sine. If you leave the sine out, then write everything else in terms of cosine, and then make the substitution. So I'll write that here and do a u substitution. Okay, so those are kind of the strategies if you have different powers on sine and cosine. But you can always use any of those identities we've talked about at the beginning. The double angle, sometimes you might see that show up. You might see an identity you want to use for that. But that's kind of the strategy when we're looking at things in this form, when you have sine to a power and cosine to a power. So I think we'll stop there for today. All your problems should be with sine and cosine. You'll use one of those probably identities from the beginning that we talked about and one of these strategies. So the first part of 7.2 part 1 should be due tomorrow and deal with those sines and cosines. And tomorrow we'll deal with some of the other trig functions. So I'm going to send around the attendance. Just make sure you sign that. And I'll leave some time if you have a little bit extra time. If there's a problem you want to see from the homework yesterday, I'll go over that. Otherwise, just make sure after you sign attendance to leave your homework and you are free to go. Yeah, did you have one, Joel? Yes, 61 is kind of a review from Calc 1, so let's take a look at 61 if you want to check that. And if I do in class, you're welcome to redo your problem and turn it in with the correct answer, or maybe you already know how to do that one, which is fine. Let's remind myself of 61. Okay, so this one said you have to rotate the curve about the y-axis, right? And you have to find the volume. And you're like, what was happening? Okay, so we're going about the y-axis. I'll just draw a little picture for you here. So this is the cosine function. Let's see, the normal period is 2 pi. So that one's probably going to look something like this. I think if you graph it, doesn't it kind of look like this between 0 and 1? Kind of goes like that. I think is what it looked like. So if you rotate it about the y-axis, you're kind of rotating it like this, right? So kind of rotating around like that. So we're actually kind of going to base it on the following formula. So the formula for volume, this is from Calc 1, is basically we're taking the circumference times the height for volume. So we're going to take 2 pi x times the f of x is the formula for this volume here. So this is your circumference, so what's the distance around, and then you're multiplying it times the height is basically what you're doing. So that's what you'll end up doing on this one. So if I were to set that up, this will be 2 pi x doesn't change, but we'll go from 0 to 1. So remember, for our x's, we're going from 0 to 1. We'll have 2 pi x, and then our function, f of x, is really the height. So the height all the way along here is just this cosine value, cosine of pi x over 2. So if you set it up like that, you were doing it correctly. Anyone set up like that? Got it? Awesome. Okay, remember from Calc 1. So that's how you have to do it. And that's how you do it when you go around the y-axis, kind of the easiest way to set this up. And then this, you'll probably have to use some integration by parts. So you can separate out the 2 pi, and then you basically have x times this cosine of pi x over 2. And so then you'll want to do that by parts. So I think, did you let u be x, I think is the easiest, right? And the dv cosine of pi x over 2. So then du is dx, and v is the integral cosine, so that should be sine, right? But you've got to divide by the pi over 2, so there's going to be a 2 over pi in front. It should be sine of pi x over 2. So it should be 2 over pi sine of pi x over 2. And then we'll go ahead and do the volume. So you have this 2 pi in front. And we're going to go ahead and do the integration by parts formula. So uv. So uv will be x times 2 over pi sine of 2 pi over, or pi x over 2, that's awkward to say, and then minus the integral of v du, which is 2 over pi sine of pi x over 2 dx. We're getting close here? Hope so. So I've got 2 pi, and then I just need to integrate this one more time. Let's see what we end up with. So if I integrate this one more time, the integral of sine is negative cosine. So this should become plus. But I'm going to have to divide by pi over 2 again, right? So that makes 4 over pi squared. So 4 over pi squared cosine of pi x over 2. And then you just got to plug in your limits from 0 to 1. That seems fun. Okay, actually, before I plug in the limits, I see that some of this will cancel, so maybe I'll distribute this through. Make it a little simpler on myself. Here the pi's cancel, and I'm going to end up with 4x sine of pi x over 2. This, let's see, will make 8, and one of the pi's will cancel, so I'll have 8 over pi cosine of pi x over 2. And that's from 0 to 1. So what do we get in the end here? If I plug in 1, this is 4, right? 4, what's the sine at pi over 2? 1. So that'll be 4 times 1 plus the cosine, though, at pi over 2 will be 0. So that part will be 0. When I plug in 0, makes this whole thing 0, right? And the cosine at 0, though, is 1. So that's going to be 8 over pi times 1. So what are we left with? Looks like a 4 minus 8 over pi. If you got that, you were right. And that's the work to get there. That might have been the back of the book, but that's how you get there. All right, good one. Yes. All right, any other ones? Just a question about setup? I'll tell you which formulas you should know for the test. I don't know if that one's on there, so yeah. All right, actually, I might need to stop because I see